Pode começar, professor, à vontade.
Okay. So, hello everybody, good afternoon. I'm going to start now. Today we're going to talk about hydroelectric and wind power plants. Okay, I think it's going to be a little long, this class, so I'm going to run a little bit. If you have problems with this, please stop me and ask questions, okay? So let's start by describing the scenario around this type of generation, electricity generation mostly. But before, I just want to say, to more or less give you a highlight of what's coming up. The importance of hydroelectric and above all, the importance of these water reservoirs is their usage as systems for harmonizing with intermittent sources of electricity. So that's the importance. We're going to simulate, at the end of the class, we're going to simulate the operation of 3 hydroelectric power plants in series in a river, and to give you an idea of how you can optimize the operation of the overall system. I'm also going to talk a little bit about how things are done here in Brazil, about the national operator, and just a little bit about how energy is sold and bought here in Brazil. So forgive me if there are some terms and words that are specific to the Brazilian scenario here, okay? And especially if the translations, because I'm trying to translate Portuguese terms to English, so forgive me if the term is not proper. Okay, if there's some doubt about these terms, please interrupt me and ask me about it. Okay. Okay. So first, just a few words about electricity generation in the world. I have this pizza graph to show you the primary sources. They are mainly non-renewable sources, coal, natural gas, and well, you have solar, wind, and wood and geothermal, which are not specifically related to climate change, but you see that the most part coal, natural gas, and oil is the most part used in the world. Brazil has a very different scenario. And I'm showing in this picture, this pie graph, just to show you that from all these sources, okay, you have hydropower and wind power is responsible for a small percentage, okay, 6.7 and 4.2. And even these percentages are small, they play a very important role, as I'm going to explain. I hope I managed to explain to you during the class today, okay? I'm going back one slide just to emphasize that when we look at these types of sources, you can also think about what's behind, or what kind of machine you use, okay, to transform the energy content of these sources, okay, to electricity. They are mostly based on turbines, okay, so that's what I'm showing you here, okay. You use turbines to transform the energy content. It may be specific heat, for instance, but it may be momentum in the case of wind, or gravitational energy in the case of hydropower. But you need a machine, a turbine, in order to transform this energy content to electricity. Okay, and when we talk about hydro and wind, those turbines are called impulsive turbines, or impulse turbines. Okay, so what's that about, impulse turbines and so on, or what's this little number here, R equals 0? So my point is that if almost 99% of all these generation here uses turbines, it's very important to know how turbines work. Okay, so that's my point today. I want to show you how turbines work and how we can use this information in order, for instance, to optimize those systems of hydropower generation, okay, or specifically water reservoirs, okay. So we call impulse turbines that are based on momentum change, okay. So let me just make a sketch here. This kind of turbines, for instance, you have momentum here, okay, mass times velocity, okay. If you have a change, you have a blade here, for instance, that change direction of this momentum, okay. So it simply change direction, okay. By doing this, you know there's going to be a force, okay. In order to do this, the blade has to apply a force on the wind, okay, and the reaction to this force is the force that is going to be used to generate electricity. Those turbines are called impulse turbines. This small number here means reaction ratio, okay, so it uses only momentum, change in momentum in order to generate electricity, okay. Those turbines are very common, as I mentioned, okay. Wind and hydroelectricity use impulse turbines. I put some here. Wind turbine, everybody knows, but you also have vertical axis turbines, as it is shown here, okay. Let me get my pointer. Those are the most efficient ones, but those types of turbines, vertical axis, for instance, they are more appropriate for low noise applications. For instance, for urban generation, because you have concerns about noise generation, so you may think about sacrificing a little bit the efficiency of conversion in order to have lower noise levels, okay. Water turbines, they are very different because, well, we're going to look this in detail in a few moments, but I have some types here. Those types of turbines are more appropriate for high levels, or very big difference between the lower and the upper level of water, okay, and those are more appropriate for very big volumes of water at low levels, or low delta H, okay. You also have, well, let me go to the next slide. You also have, just to give you an idea of the types of turbines, okay, you have fully, so those are impulse turbines, those are reaction turbines, okay. Purely reaction turbines actually use the difference, uses the thermodynamic energy of the fluid, okay. So if you have a very high difference, a very huge difference in terms of temperature, for instance, temperature and pressure, okay, so this means that, and you don't have quantum variation, momentum variation, okay, those are reaction turbines, which is characteristic of rocket engines. So I'm showing you a picture here of an airplane, actually a spy airplane, which flies at Mach 6 or Mach 5. Okay, so are very high speed airplanes, and they use pure reaction turbines. Okay, and you have turbines of mixed type. You have some difference in terms of momentum and also in terms of thermodynamic energy. Okay, so those are called Parson turbines, and the reaction coefficient is 0.5. Those turbines here you use mostly for steam and gas turbines. So those are steam and gas turbines. We're not talking about these spy airplanes. We're not talking about these steam turbines. We're talking about pure impulse turbines, okay, which are 100% used in hydroelectricity and wind power generation. Okay, some characteristics, important characteristics here are given here. So regarding wind turbines, the generation cost is very low, 8 cents per kilowatt hour. Okay, in the case of wind, the potential is virtually unlimited, as I'm going to show you in a few moments. Okay, so the potential for growth, I mean, is virtually unlimited, okay, and it has complementarity with other types of energy generation, especially with hydroelectricity, okay. A problem related to wind is its intermittency, okay. Wind is an intermittent type of generation, and this is a problem. This poses a problem because you have to do something in order to supply a constant amount of electricity 24 hours a day. So you have to have some system, as I'm going to show you, in order to regularize this intermittent supply of energy, okay. A few characteristics related to hydroelectric turbines. The generation cost is even lower. That's the lowest generation cost, actually 4 cents per kilowatt hour, okay. Its life cycle is very, very long. You may reach 100 years. You have turbines which are almost 100 years old, okay, so their life cycle is very long. In addition, this is very important. I should even highlight this point here, okay. Yeah, my color is not appropriate, so I'm going to use my pen. It has hydroelectricity generation. Usually, it's not 100%, but usually it has a reservoir, okay. You may generate directly from a river, for instance, but I'm talking about water dams, okay? And the reservoir has a functionality, and that's the central point of my talk today, okay? The importance of having these water reservoirs in a multi-source system, okay? Especially if some of those are intermittent. Okay, the idea I can anticipate a little bit is that these reservoirs, they work as energy reservoirs. Okay, so that's the main importance of hydroelectric generation. Okay, and a problem related to hydroelectric, because everything is fantastic, the cost is very low, its life cycle is very long, but I'm going to show you, we're going to make some calculation. Its growth potential is very, very, very limited, okay? You cannot think in terms of supplying the world's or significant amount of energy from hydroelectricity, because the potential for growth is very limited. I'm going to show you this in a few moments, okay? So just to still describing the scenario, I want to show you, because Brazil, yeah?
Professor, I have a question.
Yeah, go on.
Those turbines, what material are they made of? Is it cast iron or stainless steel?
Well, it depends. In the case of wind turbines, you may build from fiberglass, okay? These turbines, so you can make these blades from fiberglass, and these types of turbines for water, you usually use stainless steel. Okay, I'm going to show you some pictures of those turbines, but that's the case. So stainless steel for water turbines, and well, a light material for wind turbines. Okay, so composite materials, fiberglass, and so on is very appropriate for wind turbines because they are resistant and very light. Okay. Okay. So yeah, just a word about how things go here in Brazil, because we have a very different energy mix. In terms of electricity, okay, in terms of electricity, most of our electricity is generated from hydropower, okay, 70.6%. This is very interesting, very good, because it's a renewable source, okay. It's solar energy, it's still solar energy, because it's the sun that, the energy of the sun that takes the water from the ocean, for instance, and transport this water to high ground, so when they flow back to the ocean, we can get some energy from that. Okay, so it's still solar energy, but well, the percentage here in Brazil is, I think it's the biggest in the world. Okay, but we had a problem a few years ago, because I'm going to talk about today. If you put all your eggs in a single basket, you may have problems. Okay, so our eggs are concentrated on hydroelectricity, and you know, the amount of rain may vary during the years. Okay, so a few years ago we had some problems, especially between 2013 and 14. Okay. The amount of water available for electricity generation decreased significantly, okay, and we have to put in operation thermal power plants. In these power plants, they run basically from here in Brazil, I mean, from petroleum, with petroleum and natural gas. So simply doing this, okay, putting in operation these power plants in order to supply, okay, it changed a lot our electricity mix. Okay, you can see here, for instance, comparing 2013 and 14. Okay, you can see that hydroelectricity decreased from 70 to 65%. Okay, let me get my pointers. I think it's better. So this decreased, and the rest, especially coal, you see coal from 2.6, it increased to 3.2. Petroleum, oil, heavy oils, from 5.3 to 6.8, and natural gas from 11.3 to 13. So our energy grid, I mean, I wouldn't say deteriorated, because it's still very good. 65% is still a very good number, but that's not the tendency that we would like to be seeing. Okay, so we have these thermal power plants in order to supply this. Okay, but you have to do something to avoid this, because in addition to this, these thermal power plants, they are very inefficient, because they are built just to be used during 1 week or 1 month, not during a whole year, for instance. So they are very inefficient power plants. Okay? So you see that the importance of managing, okay? I'm going to talk today about managing this resource here, okay? In order to avoid or to minimize this type of problem, okay? Okay, let me move on. Let me talk about electricity generation in terms of potential. I'm going to compare the potentials of electricity generation in Brazil and in the world with the potential of hydroelectricity generation, okay, in the world. You're going to see that it's very limited. Okay, wind generation in Brazil, well, this is what we call the wind map here in Brazil, the atlas of the potential, wind potential, Aeolian potential in Brazil. Okay, you see, well, in the darker colors represent higher potentials. Okay, so you see that it's mostly concentrated here in the northeast coast. Okay, and you also have here, let me zoom here, let me see if I can zoom. Okay, and you also have here in Piauí, between Piauí and Ceará, you have Chapada do Araripe, because the potential here is very, very significant, very important, but the opportunity cost is high, because you can exploit tourism, for instance, here. Okay, so here, by contrast, here near the Chapada do Araripe, because it's semi-arid region, the opportunity cost is low, so it's very appropriate for wind generation here. Okay, let's just see some numbers. The total generation, okay, 71 gigawatts. Okay, so it's very high. The potential is 143. In 2014, we had only almost 10 gigawatts. Okay, and hired in and to 235, another 10 gigawatts, okay? So I'm going to show you also, I said I'm going to talk a little bit about how energy is commercialized here in Brazil, so I'm going to talk about those energy bits that I'm sure you hear on the television and newspaper, okay? So what this means and how can we calculate these numbers, 10 gigawatts, okay? Another important point here is the capacity factor of our wind potential is a little bit higher than the world average, 38%, okay? This number, 38% means, I have to unzoom in order to write something down. The capacity factor, what's its definition, okay? Capacity factor, that's, well, in Portuguese, okay, the capacity factor is equal to the installed power, okay, that's the power, the maximum power of your generators, okay, and the actual power, generated power, okay, actual. And why is that? Because wind is intermittent, so you don't have wind all the time, okay? So the average, let's say the annual average you have here, and the maximum. If you had a wind 24 hours a day, 30 days a week, and 12, sorry, I mixed up the numbers. But if you have constant wind during a whole year, 24 hours a day, you would be generating this number here, okay? And so what you really have is what goes here. So the capacity factor is what you can expect to obtain from a certain place. Okay, so in addition to these potentials here, let me zoom again. Okay, let me zoom here. Where can I? No, sorry, I mixed up things here again. Excuse me. So in addition to the potential, you see those colors here, they represent actually wind speed, okay? So black and blue is more than 6 meters per second, okay? Orange from 4.5 to 6 and so on. São Carlos, just to give you an idea, our region here in the state of São Paulo ranges between 0 and 3, for instance. Okay, I know that São Carlos and Campinas it wins a lot. So, but we are not even orange. Okay, we are yellow, or we are around here in the state of São Paulo. Okay, the potential for wind generation here in the state of São Paulo is low, except for here you have the Mantiqueira. Okay. But that's the potential. I'm going to show you in a moment. I'm going to show you the equation, what this means, how can you transform this in kilowatts of electricity. But in addition to this number, you also have to account for the intermittency of the wind. Okay, and what I'm saying is that the average Brazilian intermittency is a little bit higher when we compare that with other sources, which I'm doing here. I have a enlarged picture here, okay? So this graph shows you the intermittency of different kinds of generation, okay? Nuclear, you see that it varies during a year. You may ask yourself, why does nuclear generation varies in time? Because you have to stop, for instance, for maintenance. You have several types of problem that makes you that renders impossible to be 100% constant generation. Okay, so it's not a natural oscillation is natural. Okay, geothermal energy is the most constant one, typically geothermal. Okay, and you see wind here in black. Okay, this black curve is the wind generation in the world, and you see that our average is represented here in dotted. Okay, it's 38%, and it's visually a little bit higher than the world average. Okay, so we don't have a lot of wind sources, but they are very stable. This capacity factor is a little bit higher, and we have, well, 143 gigawatts I don't know if you have idea about this number, but this is almost 10 Itaipus. Okay. Yeah. Now some words about hydroelectric potential. Okay. So these numbers that I'm showing you, okay. So you see here. Let me zoom. Okay. Let me see if I can manage to. Again, I'm having some hard time in order to show you. Okay, so in North America, let's compare by continents. Okay, so the number in the top here is what is already installed in terms of hydropower, and the number down here is the remaining potential for hydroelectricity generation. You see that in the United States you have 0.18 terawatts already installed, but the potential is a little less than that, 0.11 terawatts. Okay, so you see that the potential is not very big. Okay, the world consumption, just to give you a comparison, is around 18 terawatts. Okay, 18 terawatts. So these numbers we're comparing with 18. Okay, so the potential for growth is only 0.11. It's very restricted, very limited. In Brazil, in South America, 0.14 already installed. Okay, and in our potential is 0.23, so we have some potential more than what is already installed, but it's still not. We are comparing this with 18. Okay, it's still small. Africa, you have almost nothing installed. Okay, 0.026 and a small potential 0.16, 17. Okay, in Europe, almost all water courses are already exploited. Okay, 0.17, and the potential for growth is 0.09, very limited. Okay, in Asia, 0.34, and the potential is 0.34. Okay, 0.341. 340. Okay, so almost 50%. You see that the potential is very limited. So that may pose a problem. We're going to see this. Okay, and the world consumption depends how you measure it. Okay, it's bigger than this. Okay, I hope I managed to describe a little bit the scenario regarding wind generation, what types of machine that you need to use, and especially the importance of knowing how these machines work. Okay, so I'm going to spend a few time here describing how these machines work, just to prepare. Okay, to develop some working equations to prepare for the simulation that we're going to do at the end of our class. As I mentioned, I'm going to explain how can you operate a system of wind turbines or combined with water turbines. How can you operate the system in order to take the maximum, in order to maximize the electricity generation. Okay, I'm going to do this. So I'm talking about what we call in mechanics flux machines. Okay, so those are machines that somehow extract energy from a flux. Okay, a flux of water, a flux of wind, and so on. Okay, so let me just draw something here. Yeah. So the idea is that since we are not talking about reaction turbines, okay. The temperature, so you have a flux here, okay, and somehow you're going to generate electricity from this wind, but the temperature, okay, is not going to vary. Okay, so if this is 25 degrees, you still have 25 degrees here. Okay, so those are flux machines. Okay, so by contrast, in a steam turbine, for instance, you may have let's see, you may have steam at, I don't know, 150 bar here, 300 degrees, okay, Celsius, and at the exit you may have 1 bar and let's say 100 degrees. Celsius. Okay, so most part of the energy, usually in this kind of situation down here, we disregard the kinetic energy component of this energy. We consider only, because it's 1,000 times bigger, okay? So we consider only the thermodynamic components of the energy content of the flux. Okay, so I'm not talking about this right now. I'm talking about this type of generation here, okay, in which you don't have temperature variation during the process, okay? Okay, so what are the equations? Well, they don't have how not to be based on the first law of thermodynamics, so I'm recalling the first law of thermodynamics, okay? And just to show you the thermal component of energy, okay, remember this is the energy inventory, okay? So you have heat and work going in and coming out of the control volume of your system, okay? And you have energy associated with this mass flow rates here, okay? And what I want to highlight this, because this expression you already know, are the components, okay? You have a component associated with thermal energy, we could call it like this, thermal energy. It's associated with temperature, okay? And you also have components associated with mechanical energy, okay? So they are related to gravity, okay? So gravitational energy, and related to, kinetic energy, okay? So what we are talking about is, or what we're going to analyze here, are turbines that use these components here, okay? These two components here, what we call mechanical energy. You're going to see that wind turbines, they use these components, and water turbines, they mostly use these components, okay? In most of the cases. So that's what I'm going to show you. Okay, and for our cases, okay, for that we're going to analyze today, everything is permanent. Okay, we're analyzing in permanent regime, so this is 0. Also, it's adiabatic. There's no heat exchange. Okay, so this component is 0. And since the temperature is the same, these components will cancel out each other. Okay, they are the same. So when you subtract here, they will cancel. Okay, so what we have here is only the mechanical components. Okay, sorry, let me just explain something. What is being cancelled, because remember, enthalpy is internal energy plus pressure times volume, or in terms of density, okay? Internal energy plus pressure divided by density, okay? So what cancels out is internal energy component, okay? So from the enthalpy, what remains is these pressure components. So we end up with this expression for the internal energy, okay? Just to be more precise in these equations, okay? So this represents, this is our working equation that we're going to use to analyze a wind turbine and also a hydraulic turbine, okay? So let's do it. Let's do this. Let's apply this for a wind turbine, okay? So we start by defining a control. Actually, I'm defining 2 control volumes, okay, or 3 actually, okay. It's represented here in blue, this blue dotted line. So we have one control volume here, which is this external frontier here that I'm highlighting, okay. This is the first control volume. The second control volume is here, the entrance to the turbine, okay. So 1, 2. Okay, this is the second control volume, and the third control volume is from the turbine to the exit here. Okay, 3, 4. So we're going to write down equations for these 3 control volumes. And the describing parameters, you have the wind speed here, V1, okay, And the idea is that, remember, this is a reaction turbine, or sorry, impulse turbine. So somehow the momentum is being changed by the turbine. Okay, so the turbine exerts a force on the wind, so it decreases its speed. Okay, so the speed is being decreased from V1 to V4. Okay, and the reaction to this force is the force that is going to drive the blades. Okay, the torque that is going to be used to generate electricity. Okay. Okay, so the point here is that V1 is smaller than V4 is smaller than V1, and since the mass flow rate is constant, the area here, back here, has to be greater than the area here. Okay, in order for the mass flow rate to remain constant. Let me just write down this equation. Sorry. So since mass flow rate is constant, and mass flow rate is density times velocity times area. Okay, the density is constant because pressure and temperature is not changing. Okay, the velocity, we know that it decreases because of the action of the turbine blades. So if velocity decreases, the area has to increase in order for the mass flow rate remain constant. Okay, so that's why I drew the area here at the exit a little bit bigger than the area here at the input. Okay, another thing I want to describe is the pressure and velocity along some lines here, or along a line here from the entrance to the exit. Okay, if you could measure these velocity and pressure, you can always do this. Okay, you would see something like this. Okay, as I said, yeah, go on.
I lost signal. I lost the background.
Yeah. From our conference, I can do nothing about that except verify that on.
Okay, YouTube.
Yeah, I'm still transmitting, but let me see. Let me see on YouTube. Yeah, it's still being transmitted through YouTube. Okay.
Okay.
So I hope you get a signal in a few moments. Okay. Okay, let me continue. I was talking about measuring the velocity of the wind and also the pressure along these lines here. Okay, so velocity, as I said, is decreasing from the left to the right. Okay, from V1 it's decreasing to V4. Okay, and you have a continuous line here because you have continuity. Okay, the mass flow rate cannot change. Pressure, on the other hand, you have this jump here. Okay, since velocity is decreasing, pressure is increasing. Okay, and you have a jump here, a step here. Okay, and it goes to the maximum at the exit. This step here, this difference, is multiplied by the area of the windmill, gives you this force here. Okay, which is the propulsive force that's going to be used for electricity generation. Okay, so the reason why you have this step here is force due to the force applied by the blades. Okay, let's move on and write down our equation. So the force, this force here, you can write it as P3 minus P2. Okay, the difference in pressure from 3 to 2. Okay, multiplied by the area here. Okay, and we know by the second law of Newton's second law that this is equal to momentum variation. Okay, so m times delta v, v1 minus v4. Okay, we can use this equation. Okay, this is not it's still not energy balance. Okay, it's a momentum balance actually. okay? And we can use this equation, okay, combine in, let me just explain where I want to get to. I want to define a way of calculating an average speed for using our assessments, okay, of the wind potential, for instance. If you divide, I forgot to make a formula, important formula, you can define a kind of a power density of the wind, okay? So if you divide W by the area of your windmill, you have small W, okay, in watts per square meter, okay? And that's the potential density of the wind, okay? So if you want to generate, I don't know, 1 gigawatt of electricity from wind, okay, and your wind is 6 meters per second in that particular place, okay, you can use these numbers in order to calculate the amount of area that you're going to need. And area means number of windmills, okay, that you're going to need to generate that amount of power. Okay, so that's how you use this part. But this is a theoretical maximum. You're going to see that you still have to multiply by the capacity factor, okay, because this amount is instantaneous, obviously. So if you manage to, if you have this during 24 hours a day during the whole year, okay, but that's not a reality, that's not a practical, okay. So let's move on, and what's going on here? Let me show you the application of this formula. As I was mentioning, suppose you have 9 meters per second, that's your average wind speed, and that must be in Patagonia, for instance, okay, because it's a very high wind speed. And you have a 20 meters diameter mill, okay, so that's it. And since I'm going back one slide, since C for maximum generation is 1/3, okay, this means that the velocity here decreases, divided by 3, so 9 divided by 3 equals 3, so the wind speed at the exit is 30 meters per second, okay. And if you want to calculate the maximum or the instantaneous power at 9 meters per second, okay, you use this formula, okay. And this strange number, 16 divided by 27, that's what I wanted to justify in the previous slides, okay. So that's the density of air. Area is the area of a circle of 20 meters diameter, okay. So you do the calculations, you find out that you can generate almost 160 kilowatts with this windmill, okay. This is a significant number, but remember, this is comparatively high speed, okay. As I mentioned, this must be in Patagonia or in Greenland, for instance, okay. And if your capacity, yeah, go on.
What happens at lower temperature? Let's say you have 9 meters per second.
It's lower temperatures increases the lower temperatures affect the density, okay. So the density at lower temperatures is higher, so it's going to increase, okay. We can do this calculation right now. For instance, I'm going to stop my presentation and I'm going to calculate the density of air at these temperatures here. Suppose, because I mentioned this must be in Patagonia, so let's calculate that near 0 degrees, for instance. So let me choose pseudo-fluid air, so I'm working with air, and let's calculate the density at 25 degrees 1 bar, that's the example I showed you, and 0 degrees 1 bar, okay. So you see density varies from 1.16 to 1.27, okay. So here in these calculations this number 117 is going to change to, sorry, it's going to change to, so 1.17 is going to change to 1.30 or something like this, or 128. Okay, so this number, okay, so this number here is going to be 1.28. So it's going to increase a little bit this power here. So it's better to have lower temperatures because the density is higher. Okay? It's okay? Okay. So yeah, that's an example of how these equations must be used. Okay? You also remember this is the maximum. Yeah. You should multiply this by the capacity factor. Okay? Capacity factor, which let's say here in Brazil is 38% in average. So you're going to get roughly, well, you see a smaller number. Okay, that's it. So here, the number that you obtain here, just to start using the terms that we use here in Brazil, the Brazilian jargon, is what we call physical power. Okay, let me see. So I'm going to write it in English. Physical power. Okay, so this physical power, and that's the Brazilian term. Okay, that's the average power that you can get in a year. Okay, so if you're going to sell this energy to someone, you're not going to sell this number. Okay, you're going to sell this one. Okay, because that is what you can expect from this statistical number here, the capacity factor. Okay, let me move on. So just to still develop these equations. Okay, so that's the formula that we deduced for the wind generation in terms of C, which is, remember, that's the relation between exit to input wind velocity, okay, what we call power coefficient. Okay, so wind power is this number. It's impossible to extract this 100% of this power from the wind. Okay, it's physically impossible. Well, by design, as I showed you, okay, by design, the power coefficient can be made to be equals to 1/3, which maximizes the power coefficient. Okay, if you plot the power coefficient, if you plot here, you see that the maximum value is attained when C equals 1/3. Okay, just to show you this. Okay, and when you replace 1/3 in this formula, you get 16 divided by 27. So that's why you have that strange number 16 divided by 27. And just last word here, you make this equals to 1/3 by design. Okay, that's you can define this by design. Okay, by designing properly your blades and so on. Okay. Okay, so let me talk about how this is done. How can you can assess the capacity factor? Okay, because capacity factor, as I mentioned, is related to the intermittency of the wind. Okay, but when I say intermittency, this is well, it expresses an idea that things are changing during time. But what is changing? Okay, you have several aspects of the wind that can change and that can affect the generation of electricity. Okay, so you may have the intensity of the wind speed may vary. Okay, so this length here of this vector, okay, may vary, but also the direction from which the wind is coming may vary in time. Okay. So what people do, for instance, I remember in Chapada do Araripe some years ago, or some good years ago, the researchers installed this kind of anemometers in several places in Chapada do Araripe, which collected data on wind speed, okay, and wind direction. So this small mill here measured the wind speed, okay, and this kind of arrow here measured the wind direction. So you had these towers installed in several places in Chapada do Araripe, and they were collecting data for some years. They are still collecting data, actually, okay. And after some years, some years of data collection, you can build statistics, and that's what I'm going to show you, okay. So the point is, the intensity of the wind can vary, and also the direction, okay. And we can generate an efficiency number, okay, like this. So that's the actual power that you get from your windmill divided by the maximum power, which is, well, the wind capacity multiplied by the maximum power coefficient in English. Right? CP is for coeficiente de potência in Portuguese. Okay, sometimes I mix the terms. Sorry for the mix Portuguese and English. Okay, so that's the definition for wind power. And let me see what I have. Yeah, this slide here shows you actual data. Okay. For the wind speed, for the intensity of the wind, okay, so in meters per second. I don't know if you managed to see here. So that's the intensity of this vector, okay. It varies during time, and if you, well, you can make statistics as I'm showing you. So the average during this period is 9.8, it's a very, very high velocity, okay, and you can if it's a normal distribution, okay, you can calculate the standard deviation, and for instance you can anticipate that the lowest amount is going to be 9.8 minus 3 sigma, okay, the smallest amount of energy that you generate. But well, this is okay. This signal here is being used to assess this number, 9.8, but another statistics, because the idea here is that the anemometer is measuring the intensity of the wind, but also the direction of the wind, okay? So here in this other slide, for instance, we, yeah, I forgot to change here, sorry, there's a small mistake, but I wanted to plot here, for instance, this number, phi, okay, or phi in English, so. Okay, so the idea is that the wind comes from the left or from the right, so it's varying. You know, let me do some drawing here. You know that the windmill, it can realign, if the wind direction changes, it can by itself realign with the wind, okay? But this takes some time because of the inertia of the windmill here, okay? And why this is a problem? Suppose that, for instance, your windmill is here are your blades, okay, and the wind was coming from here. So the windmill is aligned with the wind, so you have a zero deviation, okay. But suppose that instantaneously, I'm going to change colors. Let me get some other colors. Suppose that instantaneously the wind starts coming a little bit tilted, like this, okay? So the projected area of your wind generation, of your windmill, is smaller, and it's going to be smaller for a certain time until the windmill manages to realign itself with the wind, okay? So this time during which the windmill is not aligned with the wind, okay, you have a loss of efficiency because you have a smaller area, and also because of other effects that I'm going to comment in a few moments, okay. So this is why the variation of the wind direction decreases efficiency. And if it's varying, sometimes it's coming a little bit from the left, sometimes wind is coming from the right, if it keeps changing from left to right, so you see that the amount of time that your windmill is going to pass, okay, perfectly aligned with the wind is decreased. Okay, so this is why it's very important to have a regular wind in terms of direction. Okay, you may have a very high velocity wind, but if the direction is varying a lot, as I'm showing you here, okay, so it's going to lose efficiency. Okay, so that's the importance of having regular winds. And well, this, yeah, go on.
Is there a possibility of building a windmill that has the ability to change according to the direction of the wind? Is it possible?
Yeah, they do this. Actually, this type of mill here, they do this. Okay, this type of mill, they do automatically. Okay, but the point is that this realignment is going to take some time. Okay, it's going to take some time. And during, let me explain better this. I'm going to create a blank slide here in order to draw something for you. Okay, so as I was saying, suppose that here we have time. Okay, time, and here is the difference in terms of alignment, delta phi. Okay, delta phi is the alignment of the windmill compared with the wind direction. Okay, so the idea, no, sorry, let me change a little bit here. So the idea is that, so here is time. Okay, let me get another card. So if you have perfect alignment during all the time, so it's going to be like this signal here. Okay, if the wind changes, as I was saying, if the wind changes, the windmill can realign, but it's going to take some time. So the wind changes and you have a deviation during some amount of time. Okay, and the point is that during this period here, from this instant to this, you have decreased conversion efficiency. Okay, so all windmills, they are built to realign with the wind automatically. Okay, but depending on the geometry and the configuration of this mill, this may take some time. Okay, this is clear for you? Okay, so okay, so yeah, let me move on. And I want to talk now about other factors causing efficiency losses, because as I was elaborating here, you have a problem related to the direction of the wind. Suppose, oh sorry, so you have wind coming from a certain direction and your mill is slightly misaligned with the wind. Okay, you have other types of effects. For instance, what we call wingtip or wing effects. Okay, you know the blades, going back a few slides, these blades here, they are exactly like airplane wings. Okay, you have high pressure here and low pressure here. I'm going back a few slides just to show you this here. Okay, so you see that you have low pressure here and high pressure here. Okay, so that's exactly the same, and the difference is exactly the propulsive force. Okay, so high pressure here, low pressure at the wing tip, what's going to happen? The fluid is going to move from the high pressure region to the low pressure region, so they're going to form what we call wingtip vortexes. Okay, so you have these vortexes here, and they consume energy because they are using energy in order to create this circular movement. And this is a very common phenomena in airplanes. It's very easy to see. When an airplane passes, you see these types of vortexes here. Okay, if you type on the internet wingtip vortex, you're going to get very, very beautiful pictures of wing vortices. But the point here is that you have losses of energy, okay, because you're spending energy in order to create this circular movement here. And the idea was to convert all the internal energy into kinetic energy, or in this case of the airplane. Okay, so you have wingtip vortices in windmills. Okay, yeah, well, just to show you, in aeronautics engineering, if in order to solve this problem that you see here, the engineers, they develop, I forgot the name, but these small structures here, this winglets, they are called winglets. Yeah, winglets. They develop this kind of devices which generates an opposing effect. So they tend to cancel this vortex, but they cause drag. Okay, so it's a trade-off solution. Okay, another possibility is, well, if the problem is at the tip of the wing, let's build a wing without a tip. Okay, okay, so you build this kind of structure here. This is very, very optimistic, I should say. Okay, but there were some models that were built, and you can see this in windmills. Okay, so this kind of turbulence, you can call this turbulence. Okay, you can see, and that's the reason why these blades are so long. Okay, in order to alleviate the wingtip effect. Okay, because the longer, the lower the amount of energy that is going to be spent in this vortices, in the generation of these vortices. Okay. Yeah, and that also explains why gliders, why gliders, they have, let me draw something here, why gliders, they have this, I don't know if I'm going to be able to draw a glider here, but let's compare. For instance, a commercial airplane is something like this, okay, commercial airplane, and a glider is the length of the wings, sometimes it's even like this, it's much longer. So that explains why these gliders have very long wings, okay? Because, well, the longer the wing, the smaller the wing, these vortices here, okay? And that's why also these windmills have very, very slim and long blades in order to decrease this phenomenon. Some words about wind turbines. Okay, some details here to depict a scenario. First, since the longer the blade, the more efficient the windmill, because of this, because you decrease these wingtip vortices. Okay, so the tendency you see during the years is to have bigger and bigger windmills. Well, after, I know, so on 100 meters, you start having problems on building and installing these windmills, because you have to produce these blades, and you have to travel through the countryside. Okay, so where you have small roads. Okay, so what limits the size of the largest windmill onshore is actually the road systems, the size of the roads. Okay, so that is also an advantage of moving offshore. So offshore you can build very big windmills, because you have a barge here, for instance, with a crane, and you can build these very, very large windmills here. Okay, so no problem. And that's the actual tendency. Actually, you have two main factors which forces, I would say, which drives to offshore installation. The first one is efficiency, as I'm showing you. The bigger the better, but you have logistical problems here. So when you do that offshore, you don't have that kind of logistic problem, or at least related to size. The other important factor is noise generation. Okay, noise generation, it's a concern onshore because you have people living near these windmills, okay, and you don't have this offshore. A third factor I would say is the intensity of the wind that tends to be higher, and regularity of the wind also, okay, because onshore, yeah, go on.
This equipment have a lot of noise, but I think it's so silent, no?
Yeah, it's a low pressure noise, a low frequency noise actually. You don't hear it, but you can feel it. I don't know if you already felt, but this is like I would say a subjective idea. Okay, people that live nearby these windmills, they tend to not like. After I really would like to have a mill on top of my house, you know. But well, I don't know if you heard the expression, yes, but not in my backyard. Have you heard of that?
Okay, it's not so loud.
Okay, so that's it. That's a low noise mill. Okay, and you have, and you, as I mentioned in the beginning of the class, you have lower efficiency mills, but they emit a lot less noise. So this type of mill is more appropriate for urban application. Okay, so this is an important aspect. Okay, yeah, you have all the many types of geometries and strategies for making windmills. They all, well, I'm going to show you some. Some are shown here, okay? You see this type of geometry. This is also to avoid wingtip vortices, okay? Also this one. This balloon type here is actually to get to higher altitudes here, 600 meters, for instance. You cannot build this. It's very difficult to build a structure, okay, like this, a very slender structure that goes to 600 meters. So you actually put a mill of turbine in a balloon, okay. But first, before describing this, I want to show you this picture here. I'm going to zoom. Yeah. Where do I have my zoom here? Okay. Yeah, so I'm zooming here. These numbers here is what the researchers are expecting to obtain in terms of cost, evolution of this cost. Okay, so this is $4.5 cents per kilowatt. Sorry, 4.5 cents per kilowatt hour. In 10 years, it's going to decrease. It's expected to decrease to 3.75, and this decrease, yeah, that's what's interesting about this result here. Okay, so this decrease is obtained by a series of incremental gains. Okay, so you have a small gain to obtain in blade geometry, for instance. You have a small gain in order to obtain, for instance, in developing a more stable, more structurally stable towers, and this is related to the deviation, okay, the stability of the windmill, of the turbine. Okay, so you have a series of developments, incremental developments, the controlling system, the yaw system, that's what I'm talking about, and so on. The foundations, this is also to structural stability and so on. So you see, you have a very, you have significant reduction, 25% in the cost, but this reduction is actually obtained by a series, or through a series of small incremental, okay, incremental developments. And this is to show you, to justify when we state that wind generation, wind turbines is already a very mature technology. Okay, it's not a technology in development. Okay, well, these types of technology, these balloon turbines and so on, I'm going to show you another ones in a few moments, are still in development. But these very traditional windmills is already a very mature technology. Okay, you can say that. For instance, from this type of scenario. Okay, moving on, you have very untraditional windmills or types of ways of generating electricity. As I mentioned, balloons. Okay, so the higher you go, the stronger the winds. So in order to achieve high altitudes such as 600 meters, you cannot do this with a structure like a tower. So you can use a balloon, as I'm showing you here. Okay, this is being done, and you also have I would say kites. Okay, these are actually these are wings that can be its movement can be so that you can generate electricity. And this, how you manage to do this is through a robot. I think the next picture is better. Okay, I don't know if you guys, when you were kids, you had kites. Okay, here in São Carlos, I was completely fanatic for kites when I was a child. Okay, so what do you do? Okay, this is a robot for kites and for electricity generation. So it's very simple. You see this a pulley here. So what the robot does, it increases the length here. Okay, it gives some slack to the kite. So by increasing this length, what's going to happen? It's going further away and down here. Okay, so you release the force here, and the kite goes down and farther apart. Then when you do this, you have a force. Okay, so by doing this, the kite managed to generate some force. So the kites are pulling this cable here. Okay, so you have a force here times this rotation here, so you have power. Okay, so you have power. But your kite goes down, then you have to rewind the cable, okay, so that the kite goes up again. So you're going to spend some power. Okay, so you can generate power in this first phase, and you spend power on the last phase. So the idea, if you plot the power that you generate and the power that you spend during time, the idea is that you can generate power for a certain period of time, then you have to spend some power, then you generate. Okay, you see that the average is positive. Okay, so you can generate some power from the system here. Okay, so that's explained in this graph here. You have an active phase in which you can generate power, and you have a return phase in which you may or may not spend significant amount of power. Okay, so that's a technology that is being tested. You have robots to do this, that in addition to making these operations, it assures takeoff and several other types of piloting, actually, this wing, because it's actually a wing. This is another type of kite. Okay, it's a little bit different from this configuration here, because this one does this type of movement here. This one, it's a wing. It circulates like this, and during this circle you have an active phase and a passive phase, I would say, like this. Okay, in terms of energy generation. Well, this is research. It's not widespread applied. Okay, you also have. I want to start switching, because I have to hurry up a little bit. I'm going to start switching to water turbines, okay? So you can generate electricity from water, okay? From a river, for instance, like in this example here. If you have a very huge river in which it's impossible or very difficult to make a reservoir, you can generate electricity with a series of wind or water mills like this one. Okay, you can do this, but, well, this is feasible, but you know, here in Brazil, especially here in Brazil, I would say this is not practical, because here in Brazil, our rivers, they contain a lot of organic materials, biomass actually. You have trees, you have all types of debris, let's politely call them like this, debris that are being carried by the river. You may have a whole tree being carried by this river, and when these debris hit these windmills, okay, it's going to spoil. You have maintenance problems, okay. So this is a problem here in Brazil. For this to be applicable, you have to have very clean rivers, okay, and this is not very easy to get, okay, but it's possible, okay. Another problem that you have related to water, you don't have that problem in air, okay, is cavitation, okay, because since you have different velocities here, there may be some places, especially on the tips here, where the velocity is very high, okay, the velocity is very high, and you know, when the velocity is high, the pressure is low, okay, that's Bernoulli's equation, okay. So when the pressure is low, you may have water vapor. So these small bubbles are vapor bubbles, okay, and that's cavitation. I don't know if you heard the term cavitation. And the problem is that when you have a bubble formed here, okay, and this bubble is stable when the pressure is low, but if for some reason this bubble goes into a region where the pressure is high, it's going to implode, okay. So that's what happens. And when a bubble implodes, it causes what we call a water hammer. It's like hammering, like a huge impact like this related to the implosion of these bubbles. You may have very, very huge pressures associated with this implosion of these bubbles. And these can erode, okay, parts of the blades, as it is shown here, okay. So you have maintenance problems. I remember some years ago, or some 10 years ago, I visited one of these hydroelectric power plants here near São Carlos in Ibitinga, okay. And well, the turbine is very big. A person here would be something like this, okay. This is a person. You can go on the top, and we had this, right? You could observe this kind of problem. So the workers were correcting this problem, okay, because you have cavitation. Yeah?
Is there a problem in water pump also, no?
Yeah.
Cavitation, no?
Yeah, exactly. Yeah, exactly. You may have this, okay.
It's the same thing?
Yeah, exactly the same thing, okay. Cavitation related to these very huge pressure variations due to the implosion of these cavitation bubbles. Okay, so if you could see with a microscope, it's like having microscopic hammers, okay, impacting on the surface of the metal, and you have this kind of erosion. Okay. It's a very big problem even for ships. Okay, you have this in ships also. Cavitation is a very significant problem. Let me move on. Okay, so yeah, let me talk now. Since we're talking about water turbines, let me talk now about hydroelectric power plants. Okay, so I started to, the equations for the analysis we already have, it's going to be the same, but I want to elaborate a little bit more because I also want to talk about operation. Okay, I just tackled this problem related to windmills. Okay, I was talking about the deviation, the difference, where the wind's coming from and the alignment of the mill, okay, but I didn't elaborate further than that. In this case, hydroelectric power plants, I want to elaborate a little bit more to, well, in order to explain how things, especially how things work here in Brazil. Okay, so I'm going to explain a little bit about how we design a power plant like this and how we should operate these power plants in order to maximize the power generation. Okay, so let's see the scenario. In the world, you have, well, you have data from several hydroelectric power plants. The biggest one is Three Gorges in China, okay, and the second one is Itaipu in Brazil, and so on. We have a list, okay. So we're going to compare this to the biggest, the first two ones, okay. Three Gorges and Itaipu here in Brazil, okay. We're going to compare their numbers. I don't know if you managed to see, but the installed capacity in China is almost the double as what we have here in Brazil, but even though they are comparable in terms of average generation due to the capacity factor and due to the characteristics of the reservoir. Okay, and I'm emphasizing this point because here in Brazil, and we have a special concern, and this is okay, this is correct, we have a special concern with the impact, the environmental impact that these reservoirs are going to cause in a specific region. This is okay, but we must be aware that reducing the reservoirs, okay, reduces the efficiency of these reservoirs. That's the central point actually of this talk here today. Okay, so I want to not only state this, but I want to justify this through a simulation. Okay, so but let's continue with the scenario comparing Three Gorges. Here's a picture of Three Gorges in China. What I want to emphasize here that the river, okay, the river is surrounded by mountains here, okay, and this is going to affect the geometry of the reservoir. Okay, Itaipu, on the contrary, is a very flat region. Okay, so the reservoir is going to be very different in characteristics. Okay, I'm going to elaborate a little more in a few moments. Okay, so the point here, the point in showing you these pictures is to show you that the river is surrounded by mountains, okay, and hills, and in Itaipu, okay, the region here is very flat. Okay, so this is an important point I'm going to show you in a moment. Just some numbers. Forgive me with the Portuguese, but I don't have the picture. I don't have access to edit the picture to translate the term, so I'm going to say, you see, let's compare some numbers. Itaipu and Three Gorges. Turbines. So Itaipu has 20 turbines, okay, Three Gorges, 34 turbines and 6 underground turbines, okay, so 40 turbines. The installed capacity, 14 megawatts, that's the sum of, that's 20 times the individual capacity of each turbine, okay? And the actual number, the physical power, as I was mentioning, will depend on several other aspects, okay? And this is what is expected for Three Gorges Dam, okay? So it's almost the double, okay? When you compare the production, you see that Itaipu is producing more energy each year, or at least at these dates here. Well, actually, this is very out of date, okay? But what I wanted to highlight is not the installed power, because you have, I don't know where you had I think here, sorry, I'm going back a few slides, and I'm going to zoom to show you the installed capacities and the annual generation, okay? The installed capacities, you see, the installed capacity in Three Gorges Dam is almost twice as it is in Itaipu, but the generation, the annual generation is almost the same, okay? And why is that? It's not only it's due to the capacity factor, but also due to the reservoir, okay? I'm going to show you this, okay? Because, well, I came back here because the numbers here are very out of date. So the point is the reservoir. It's not the turbines. The point here is the reservoir. As I mentioned in the first slides, the functionality of the reservoirs, okay? You see the reservoirs are compared here in this other table, Itaipu and Three Gorges, okay? In Portuguese, gorges is garganta, okay? The extension, okay, since Three Gorges is in a valley, actually the extension is very significant, 600 kilometers. In Itaipu it's 170 kilometers. The area is roughly the same, okay? Itaipu is larger because, as I showed in the picture, it's a very flat region in Brazil, okay? And the amount of water stored in these reservoirs, 29 cubic kilometers and almost 40 cubic kilometers, okay? Well, this is stored energy actually, and the potential is related to the level, the height of the water, okay? So 220 meters in Itaipu and 171 meters in Three Gorges, okay? So these characteristics, we're going to simulate our final simulation. I'm going to show you a simulation. I'm going to model the system, and then we're going to change the size of the reservoirs in order to try to simulate the operation of a system with big reservoirs and with small reservoirs, okay? So the idea is to compare Itaipu and Three Gorges, or the equivalent systems. Okay, so let's see the equations for this type of generation. Okay, so you have a reservoir, so you have a difference in height. From 1 to 2, you have a difference in height. If you define a control volume, for instance, let me draw the control volume here. Imagine I'm not going to be able to draw a tube here, a small tube, but suppose you have a small tube, okay, starting here at 1 and going all the way through the turbine, and you end up here in 2, okay? So that's my control volume. I'm not going to be able to draw this properly, but you can use your imagination and imagine a small tube going from 1 to 2, and that's going to be our control volume, okay? Okay, so when we write the equation, energy conservation, for this control volume, so that's the same equation as before, okay, in which we neglected the internal energy because temperature is constant. That's the equation that you have, okay? So pressure, velocity, and gravity, okay, the Z components. So let's see, what's the pressure, or let me ask like this, the pressure in one or at 1, the pressure here is greater than, lesser than, or equal to the pressure at 2, okay? You see, the pressure at 1 and the pressure at 2 is the atmospheric pressure, okay? So it's the same. You got these terms will cancel, okay? What's the velocity at 1 and what's the velocity at 2? It's 0. It's the same. I'm not talking about the velocity here at the turbine, okay? I'm talking about the velocity here at this position and at this position. So it's 0, so these terms cancel, and what you end up with is only these terms here, because Z1 is different than Z2. So what you get by canceling these terms is that final expression here, which accounts for the power generation from a variation in height. Okay, so that's why the height of the reservoir here, or not the reservoir, because the reservoir is here, the height of the water level is important. And that's why, I'm going back a few slides, that's why, this Itaipu has a bigger height than Three Gorges, and that's why it tends to generate, from these parameters, it tends to generate more electricity, okay, because the height is bigger. Okay, so that's our working equation. We're going to apply this, okay. So that's the maximum power that I can manage to, that I could manage to generate from this variation, from 1 to 2, okay. But I also have, let's say, an actual power that I get here, okay, and the actual power that I get will depend on all the problems related to the efficiencies, to the flow through the blades of the turbine, okay. So the actual power that I get is going to be slightly lower than the maximum theoretical power, and the relation between the two is the efficiency. Be advised that when we talk about water turbines, especially very big water turbines, this number tends to be 99% and even more. Okay, so the efficiencies are very significant when we talk about water turbines. Okay, let's move on. Some numbers. I'm going to use this equation to make a very approximate calculation in order to assess the potential for hydropower generation in the world. Okay, because I already mentioned in the beginning, the first slides, I mentioned that the potential for growth is very limited in the world. So I want to get this number. Okay, so let's see how we can get this potential for growth. Okay, from very easy to obtain numbers. Okay, the average continental height, this is very easy to obtain this number, okay, is 840 meters, and that includes the Everest and so on. Okay, so let's be conservatives. Okay, let's say that the average height is 840 meters. Okay, the average rainfall in the world, that's another simple number to obtain. Okay, is 500,000 cubic kilometers. That's the average amount of rain that we get every year. Okay, and part of this at sea and part on land. Okay, so let's suppose the following: we have all this water, okay, at this height, 840 meters. Okay, so if we manage to generate electricity from all this water, and considering this height, okay, we can apply this formula. Okay, so m dot here is 107,000 cubic kilometers divided by the amount of seconds in a year. So that's this number here. Okay, 107,000 kilometers, 10 to the third meters cubed is to convert to meters. Okay, and let's say 355 days times 24 hours times 3,600 seconds each hour. So that's the number of seconds in a year. Okay, so the total number of seconds in a year, and here is the amount of cubic meters of water on land in a year. Okay, multiply this by water density. We have there's a mistake here. Let me see. That's okay. The formula is okay. Sorry. So that's the density. Okay, because this is cubic meters per second is volumetric flow rate. I multiply this by density to obtain mass flow rate. Okay, so 997 kilograms per cubic meter, that's density of water, times G, times the average height. Okay, when we do the calculations, we get this number, 27.8 terawatts. This is a very, I would say, optimistic number, because it considers that all precipitation inland could be used for power generation. And we know that's not the case, because most of the water that falls is absorbed by the soil. Okay, goes to the water tables and so on. Okay, just a fraction of this number, okay, can be used for gym, but no problem. The idea is just to have an assessment. Okay, let's compare this number that we obtained from these very simple calculations with actual numbers. Okay, the actual numbers assessed by the United Nations, okay, is this one, 3.8 terawatt. That's the maximum generation. Okay, and well, we're not so bad, because we obtained it, okay, we obtained it 10 times more, roughly speaking, but it's not 1,000 times more. We are okay, and so that's the maximum generation. Okay, and that's the world consumption. Okay, so you see that they are comparable. We have very small room for growth. Okay, so it's a problem. That's why Homer Simpson is very concerned here, because we don't have room for growth, and it's a shame, it's a pity, because as I mentioned in the beginning, it's very cheap, it's renewable, it's very its life cycle is very long. So it would be fantastic if this number was something like 30 or 100 terawatts. Okay, but that's not the case. So in conclusion here, the potential, as I was mentioning, the potential growth of hydroelectric generation is very limited. However, that's the point. They will play a very important role because of these 2 points here. First, the reservoir, the capacity of storing water for energy generation. Okay, so it's very cheap. It's a very efficient and cheap way of storing energy as water, okay, in the reservoir. And another point is its complementarity with other sources of energy, especially the intermittent ones. Okay, and this is for stabilization of supply, okay, in face of fluctuations in generation conditions, especially for those models that are intermittent, wind power, photoelectrics, and so on. Okay, and also fluctuations in demand. The last slide is going to be a sketch of how this can be done. Okay, let's try to focus on that simulation. How things are done, not only here in Brazil, but everywhere in the world. So you have rivers, as I'm showing here in the state of São Paulo. This is Rio Tietê. Okay, it's a funny river because it starts here near São Paulo and it goes inland. Most of the rivers goes to the sea. Actually, it goes back to the sea, but it's going to make a big turn. Okay, so it goes to near Mato Grosso, then it goes down. It go all the way down to Argentina. Okay, so these waters here will end in the Atlantic Ocean, but in Argentina. Okay, I'm going to show a bigger picture in a few moments. So you see, you have well, the river here in the Tietê River is completely exploited in terms of its potential. If you see the topography here, for instance, well, here we have here the ground is very high. Okay, so it decreases slowly when you go west. Okay, and so I'm gonna, let me see, I can draw here. Okay, so in São Paulo, reservoir is very high. Okay, so it goes down. That's why the river flows in that particular direction, but the reservoirs are already, so you have one reservoir here, okay, and the height of this reservoir is almost at the next reservoir here. So this is water, okay, water. So when I say it's completely exploited, that's the kind of topography that you have, okay. Let me get my pointer. The tip of the reservoir here is at the foot of the dam here, okay. It's as I'm drawing here. So you have this series of reservoirs. Barra Bonita, Bariri, Bitinga, that's the one I visited a few years ago, as I was mentioning, okay. And well, you have Três Irmãos, Jupiá, and so on, okay. If you see the whole scenario, okay, that's the whole scenario here in Brazil, and these dams in the Tietê River is represented here. That's the, I'm going to zoom out here. I think it's interesting, okay. So let's see how it's host this system here in Brazil. Okay, so Tietê is here. Rio Tietê, you see here. Okay, and that's those are the reservoir. This picture is very rich because it shows if you have places for ships to go up and down through the reservoir. Okay. It represents also, that's the capacities of the reservoirs. This graph has several different types of information, so it's very rich. Okay, so that's Tietê. Tietê goes to the, let me see, Paranapanema is another river in Paraná, okay? So they get together, and Rio Iguaçu, okay? So let's follow the water. So that's Rio Tietê in São Paulo. And all these circles and triangles and so on are generation units, okay? So that's São Paulo, is the city of São Paulo is more around here, okay? So Billings, you see Billings and so on. Where is, well, I was trying to give you an idea, but let's follow the water. So that's the Tietê River. Okay, it mixes with waters from Rio Paranapanema, okay, from Iguaçu, okay, then it goes all the way down to Argentina and then ends up in the Atlantic Ocean. Okay, so that's the whole system, Brazilian system actually. That's let's zoom again. That's the legend. Okay, power plants with reservoirs. Those are future, okay. Fio d'água, you don't have reservoirs, okay. Future and yeah, in construction and so on, okay. And the reference is given here. Okay, so this picture actually is the picture that what we call the Operador Nacional do Sistema Elétrico, the national operator of the electrical system here in Brazil. So he has this image here, okay, all the reservoirs, and you can control the operation of each of these reservoirs, okay. You can press a button and increase the flow rate in a specific power plant, or if you don't have this level of automation, you can simply telephone to the operator, to the local operator, and tell them to increase flow rate, for instance. Okay, so the idea is that you can operate the entire system from a single room. Okay, so that's the point. And the simulation that I'm going to show you in a few moments is how to operate. What's the strategy of operation? Okay, in order to maximize the overall energy production, okay, both in terms of volume of energy, but also in terms of stability of generation, okay. A few words about our institution, okay. This, I'm going to elaborate on this on the last class next week, okay. The institutions associated with the electricity sector in Brazil. Okay, so I'm talking about the operation, the national operator of the system, as we say here in Brazil. Okay, so this is the pilot, okay, in the pilot's cockpit, because this resembles a Boeing, okay, a very huge airplane, very sophisticated, very complex. So the operator is like the pilot and co-pilot, okay. But another important institution is the Electrical Energy Commercialization Chamber, CCEE. So all the electricity bids that I'm sure you hear on the news are organized by these institutions, okay? And I'm going to show you some things about CCEE here in Brazil in this class, but I'm going to show you more on the next class, on our last class actually, okay? So these two institutions are, let's say, under the umbrella of the Electrical Energy Agency, okay, which is related to the Mines and Energy Ministry and so on. Okay. Also, this is another important institution, is the Energetic Research Corporation. That's its name in English. Okay, Empresa de Pesquisas Energéticas in Portuguese. Okay, so all sorts of calculations and, for instance, the wind map was organized by this institution. Okay, so all types of studies, especially studies and research, are fostered, I would say, by this corporation, by this institution, and they are publicized. Okay, so you can increase development in general in Brazil. Okay, so I'm going to come back to this picture next week, and today I think I'm going to show just a few information about this one, and we're going to end the class by trying to simulate the problem that the national operator has to solve every day. Okay, so let me show you the information publicized by CCEE. Okay, for instance, you have, as I was mentioning, the energy bids, and what they publish. This is a print of their site. So you have all the results, okay, of the bids, the consolidated results. You click on this, and you have a spreadsheet like this one, okay, and this spreadsheet is very, very detailed. It contains a lot of details. I don't know if you manage to see that. For instance, the type, the company that sold the energy, the company that bought the energy, it's CNPJ. Okay, so you have economic informations, and also all sorts of information for every contract related to these bids. You have, for instance, the amount of energy, the total amount of energy that was commercialized. If this is to be delivered in 10 years or in 20 years and so on. If you have all sorts of information, the price, if it's going to take, if it's a bid A0, for instance, that's for instantaneous, immediate supply. If it's a bid A5, for instance, the seller has 5 years to start delivering the energy. Okay, so you have many types of information. I'm going to show you next week, and you can, from this database, you can, for instance, build this type of graph. Okay, I didn't bother to put the current data, but this graph is the total amount of commercialized energy. So physical gigawatts by physical, that's the installed capacity multiplied by the capacity factor. Okay, so this is real. Okay, and you see that in 2015, okay, 2015, that's the current date, you have, you already know how much energy you're going to have, or new energy you're going to have in the following years. Okay, so you have increased amounts, and then it drops. Okay, and the idea is that since these bids are regular, okay, these curves or this dent, I would say, it travels to the right here. Okay, so when we integrate, we have an idea. We can forecast how much energy is going to be in the market from this database. Okay, next week we're going to work with this spreadsheet. We're going to open. We're going to construct this kind of graph here. Okay, you can filter, for instance, in terms of source. For instance, if you want to know how much energy from wind you're going to have in the following 35 years, you have this information. It's very easy to filter that from that spreadsheet. Okay, I'm going to show you next week. So an example of application: optimized design and operation. Okay, in order to explain to how you can have an optimized operation, you must know, at least in rough lines, how a hydroelectric power plant is designed. Okay, so I need to talk a little bit about design in order to justify why the operation has to be that way. Okay, so I'm talking about design. Okay, first. So let's see the problem, and let's define, I would say, a synthetic problem, just to exemplify. Let's take this case just to build a scenario for us. So we have 3 reservoirs like this. Okay. That's the flow rate of the main river, 100 cubic meters per second. So that's the river feeding this first reservoir. Okay. The second, that's the height. Okay, the nominal height. I'm going to explain this. Okay, that's the second reservoir has one or some tributaries. Okay, so you have an additional 10 cubic meters per second from rivers that are arriving here. Okay, you see what I mean. Okay, let me get my pen. So you have the main river flowing that way. Okay, so you have 100 cubic meters. That's the first reservoir. The second reservoir has tributaries that contribute to 10. Okay, so 10. And the third reservoir also has tributaries that contribute with additional 20 cubic meters per second. Okay, so the final flow rate, the final total flow rate is 130. Okay, so 130 is 100 plus 10 plus 20. Okay, and those are average numbers. This is very important. Okay, these numbers are averages. Okay, the flow rates have seasonal variations, as I'm showing here. Okay, so the main river varies, its flow rate varies, its average is 100, but its instantaneous flow rate can vary. And we're going to define a variation, just to represent the actual variations that we have in order to simulate the effects. So we're going to suppose that, we're going to assume that the main river has a slow variation around 100, okay, and the other tributaries, okay, the one, I don't remember which one is which, but one of those will have, a higher frequency variation as this one, and let's say the green tributary will vary a lot in the first years of in the first months of the year, and then it's going to remain stable through the rest of the year. Okay, we're going to give some definitions, proper definitions to these variations, but that's the case here. Okay, so just to repeat, the problem is, how can I operate these dams here, these turbines, in order to maximize power production in face of these variations here. Okay, so let's see. How if we have to design these turbines, to define, specify these turbines, how this is done. Okay, so I'm going to explain you how. You see, the first thing, you have to choose the type of turbine and also the size of turbine. Okay, for each turbine or each type of turbine, you can characterize its conversion efficiency in terms of its rotation. Okay, it's practical to use what we call specific rotations. Okay, which is defined here. Okay, and capital N is the actual rotation in RPM or radians per second. Okay, so we divide by power and so on just to normalize these rotations. Okay, so that's a working form. So when you plot different sizes of turbines, okay, you have this kind of variation in terms of its efficiency. So if you choose this size of turbine, this turbine size, okay, you're going to calculate the flow rate in height and so on in order to operate in this point here, because it's the maximum efficiency point. Okay, maximum efficiency point. So if you don't know the size, and you have to choose the size, you're going to choose a particular size, but you have to choose the one that gives you the maximum efficiency. Okay, so the choices that you have are actually those points of maximum efficiency. Okay, and if you link this maximum efficiency point, you have this blue curve here. Okay, so this blue curve is the locus. In Portuguese we call lugar geométrico. Okay, locus of design points of maximum efficiency conversion. Okay, so we're going to calculate a specific point. Okay, and the turbine that goes on this specific point is the one that has maximum efficiency. Okay, so that's how things work. And what are the types of turbines? Water turbines. There are three types. Okay, Pelton, Francis, and Kaplan. Okay, in Ibitinga, for instance, is Kaplan. I don't know if you know, in Cubatão, there's a power plant called Henry Borden. Okay, it uses this type of turbine, Pelton turbines, for high altitudes. Delta H is very big. Okay, so the normalized specific rotation is low because delta H is high. Okay, so a Pelton turbine is more appropriate for hundreds of meters of delta H. Okay, Kaplan turbines are turbines more appropriate for small altitudes here, 50 meters, as we're going to use in our case. And Francis turbines is a kind of an intermediary. It's like a flex fuel engine. Okay, because it works at higher altitudes and also lower altitudes. So if you have a reservoir and you have a very huge variation in terms of height, okay, so it's better to choose a Francis turbine because you have more room for optimization. Okay, so that's our market. Let's say we have to choose a kind of turbine. When we calculate the specific rotations for the data that we have, this height, this flow rate, and so on, we get these results. Okay, in terms of specific rotation, 3.14 and 0.4. So we're going to choose Kaplan turbine. Okay, 3.14 is something around here. We could choose Francis, but I'm going to choose Kaplan. Okay, because well, I know that in Tietê River they are all Kaplan turbines. Okay, just to remain close to our local reality here in São Paulo. Okay, so we're choosing Kaplan turbines. Here's some more specific data in terms of the application, in terms of delta H, what we call head, that's from the jargon, okay, and typical efficiencies, okay. Let me move on. So let me now define the problem. The problem is that the design, as I showed you, is based on nominal parameters. Okay, by nominal, I mean annual or pluriannual averages, the average flow rate and so on. Okay, so the result is optimized. Okay, the maximum efficiency is optimized for these nominal parameters. Okay, but the actual instantaneous operation parameters vary with respect to these nominal parameters. For instance, the instantaneous flow rate varies. I'm going back a few slides. Okay, so the instantaneous, this 100 cubic meter is the annual average, but the instantaneous flow rate is varying, okay, as I showed you here. So 100 is the average, but the instantaneous flow rates can be above 100 or below 100, okay? So that's the point. So when we design a power plant, we design for these average values, okay? 100, 20, and 10, okay? But the instantaneous reality of operation may be different, okay? So that's what is said here, okay? The operating parameters vary with respect to nominal parameters. So we have this problem. That's a key point here, okay? So we have this problem. How to adjust the overall operation, okay, acting on controllable variables in order to optimize performance, okay? So how can I set this flow rate to compensate for a difference in terms of a difference with respect to the nominal parameters, okay, and so on. Okay, so that's it. That's the problem. Let's try to formulate this problem now, right now. Okay. Let's see. We have, I forgot to talk about these two formulas here. So when we talk about optimization, okay, you have to say what is going to be optimized. What do you want to be optimized? Okay. So you have what we call performance criterion. Okay. Or in terms of optimization jargon, what is going to be the optimization function? This function phi syst here, this function here, this is the function that we're going to try to optimize. So this function phi we're going to define. We're going to have to define this in order to formulate the problem. So that's what we're going to do. Okay. And let's suppose that each reservoir has one optimization function, phi. Okay, I'm going to define it in a few moments, but suppose each one can be optimized. You can define what's going to be its optimization function. And if you want to optimize the whole system, okay, if you want to maximize the whole system, you can, for instance, add these functions. Okay, so suppose phi is equal to the total energy generation during the year. Okay, so if you add up all the energy generated here, and here during a whole year, that's what we want to maximize. And the point is that you're going to see this is really going to happen. If you want to optimize the sum of three terms, for instance, I don't know, A plus B plus C, okay, you can allow, for instance, you can allow for, the perfect situation is to have all three terms going up, okay, all three terms going up. This is perfect. But you may have a situation in which, let me draw down here, okay, in which one of these go down, okay, but the other two goes much higher, okay. So by sacrificing this one, you enable a more significant optimization of the other remaining terms, okay. So that's we're going to see this happening in our simulation, okay? And this is especially related to the size, to the volume of these reservoirs here, okay? Okay, so that's it. We have during the year we have an instantaneous total generation, okay? Instantaneous total generation, and because the flow rates are varying, the instantaneous total generation is going to vary during the year, as I'm showing you here. Okay? Okay, so let's try to identify a possible single objective optimization function. Okay, so let's think about what do we want. Okay, what do we want? We want two things here. Okay, we want two things here. We want to, roughly speaking, we want to increase the average generation, instantaneous generation, because by increasing the annual average, I assure that the total volume is going to be increased. Okay, so we want to increase the average generation, the average power, okay, but we also want another thing. We want, as I was mentioning, we want regularity, okay? So we want to decrease the dispersion around the average, okay? We want to increase W, okay, but we want to decrease sigma. And sigma you may calculate as being the standard deviation around the average value. Okay, so we want these two objectives. We want these two. Okay, so at this point we identified two things that we want to optimize, and we have a choice to make now. Okay, we can formulate the problem as a multi-objective optimization problem. Okay, and we end up with a kind of a Pareto frontier. Okay, in a multi-objective optimization problem, you get something like this. Okay, so you plot W here, sigma here, and you may have a Pareto frontier, which is your non-dominant points. Okay, so that's multi-objective optimization stuff. Okay, and we're not going to follow this path. Okay, we're going to transform our multi-objective optimization problem to a single optimization problem by defining this artificial optimization function. So let's see how it works. Okay, if we want to increase W, and we want to decrease sigma, we can calculate this. We can put W in a numerator, okay, and sigma in the denominator. Okay, so when W increases and at the same time sigma decreases, that means that phi increases. Okay, that's completely artificial. We're going to have different optimization functions, but the idea is that when we get what we want, okay, when we get the behavior that we want, we can transform this in a characteristic behavior of our single objective function. Okay, so that's it, and that's a possibility. As I said, this is completely artificial. You can, for instance, have different definitions. As I said, you can square this, for instance. You have another optimization function. Okay, so the one that is written here is the one that we're going to adopt, but we're also going to have other definitions in order to verify if the definition of the optimization function affects the final result, or the final conclusion at least. Okay, so let's see. Now we have to model. So we have already an optimization function, and we're going to have others. Okay, but we have at least one. Okay, so we want to optimize this optimization function, okay, which is the sum of the individual optimization function, okay, and we also have restrictions. This is a constrained optimization problem, actually, okay. And what are our restrictions? Okay, those restrictions are related to mass balance in the reservoir, as I'm showing you here. Okay, so the variation of the total reservoir volume, K here is for the kth reservoir. We have reservoir number 1, 2, 3. Okay, so this equation applies to all 3 reservoirs. Okay, so the variation in volume is equal to the input flow rate of the main river, okay, plus the tributary flow rate minus the downstream flow rate, okay. So this is very, very simple. This is the first restriction, okay. Another restriction is the turbine performance, okay. So that's the conservation of energy. So the power, instantaneous power generated by the turbine is equal to the formula that we derived in a few slides back, multiplied by an efficiency factor here. Eta here is related to the efficiency, which is, I'm going back one slide, okay, some slides, and is related to these curves here, okay. So, and that's the central point. So you have mass balance, you have performance equations, okay, and well, if you want to assess the total energy generation, you simply integrate the total power, okay, and related to this performance, that's the turbine performance, okay, which is characterized by its efficiency, okay. So eta is a function of the specific rotation, as I mentioned. And you also have a very, very, very important parameter here, or variable to be more precise, which is related to delta H. We call head, that's the jargon, okay, but it's the height of the reservoir, or the water level, okay. And this actually relates to the volume through the reservoir. We could say that delta H, okay, is a characteristic of the reservoir performance, and this is related to its geometry, okay. So we're going to construct this model. It's very simple, okay. These curves, these eta curves, you have from the manufacturers of these turbines, okay, and this one, this function here, you can assess from the geometry of the reservoir. I'm going to show you how, okay. So well, this slide here is just to show you that this actually happens in real rivers, in real systems, okay, just to justify the following, okay. We are going to define some variations, some mathematical formulas to simulate this kind of behavior, okay. And it's going to be like this. So for the main river, we're going to have these variations, harmonic variations actually. So we have 100, it's the average flow rate, and a sinusoidal variation around 100, as it's drawn here, okay. The blue river is going to vary like this, so it's 20, okay. So it's a sinusoidal variation, okay, as well. And the green river, you have a sinusoidal variation during this period here, and then a constant flow rate. The corresponding mathematical formula is given here, okay, and the average flow rate is 10 cubic meters. So that's why we have this strange number here, 7.878. That's when you integrate this during the whole year, okay, you get 10 as the average flow rate, okay. So these definitions is just to simulate this kind of behavior, actual behavior in a real river. Okay. Yeah. So the turbine, how do we control the turbine, and how can we model this performance curves or efficiency curves? Okay. So what we can do to control the operator can increase or decrease the flow rate, okay, that is being used to generate. Okay, so this can be controlled. You open or close this valve, you increase or decrease this flow rate instantaneously. Of course, during a year, okay, this has to be equal to the average flow rate. Okay, but instantaneously you can vary this. Okay, so Q is variable or controllable. This is one controllable parameter, because I'm emphasizing this because these variations here, you don't control them. They happen, okay? They happen. So you have to, the point is, how can I change these flow rates in order to cope with these non-controllable variations in order to optimize the overall system. That's the point. Okay, so that's our controllable variable, and as I mentioned, the turbine was designed for an average flow rate or a nominal flow rate, which corresponds to maximum conversion efficiency. So when we vary this, we know that we're going to decrease the individual efficiency, but it may be increasing the overall efficiency. Okay. So in order to model this, what we're going to do, we're going to well, these ETA curves here you get from the manufacturers, okay, and we can model like this, for instance. This is again just to exemplify. Okay, so suppose that we have this kind of variation. Okay, ETA max is the nominal design point. Okay. And X is normalized rotation. Okay, so the manufacturer, I'm going back a few slides, okay, to get the, yeah. So you have for this model, for instance, you have a minimum rotation and a maximum rotation. Okay, it's nearly 2 and roughly 10 here. Okay, so X in that slide, so 0 means 2 and 1 means 10. So we're normalizing the specific rotation, okay, in order to represent this. Okay, so that's, again, this is just a way of modeling things. Okay, so that's it. Yeah, and the nominal point is the average between 0 and 1, okay, or the average between the two minimum and max nominal rotation. Okay. Okay, now the reservoir. This is the most important part, because that you get from the geometry of the reservoir, and what I want to show you today is how these affect the overall performance. Okay, so suppose that the geometric form of our reservoir is something like is drawn here. Okay, so it's a kind of a pyramid cut. Okay, so you have this form, this base, yeah, okay, and you have all the parameters. So that's the extension, that's height, and so on. So capital A, B, and beta and alpha are the geometrical parameters, okay. And what we want to get here is a formula relating delta H to the volume, okay. That's very important. So you know that the total volume is the height of the pyramid, okay, multiplied by the base area. Okay, so the height here is L, and well, the area here you can get from yeah, here. Okay, this formula. So I'm going to pass very quickly here, because the idea is not to make these calculations. You can do it by yourselves afterwards, okay? And you get this final relation here. So that's a relation between H, okay, the head of the reservoir, the pressure that's going to be used to generate electricity, and the reservoir's volume, okay? It's a complex relation because you have delta H here and here, but you also have delta H inside alpha and beta, okay, because they are given by these formulas. Okay. This is very, very easy to do, okay. So the formula that we have to use is this one, and by getting some typical results or typical numbers, we get this kind of result. So 5 kilometers extension, this is a small reservoir, okay, 100 meters, 200 meters, 50 meters, okay, these are typicals. This is typical for small reservoirs in the Tietê River, okay. So by doing the calculations, we get 0.025 cubic kilometers of water in this reservoir. And when you compare this with Itaipu, 19 cubic kilometers, and with Belo Monte, okay, 2.5 kilometers, okay, you get this these typical numbers here. Another problem that is interesting to emphasize is the effect of silting. Okay, you know you have material that is constantly being deposited on the bottom of the reservoir, and this material, solid material, it occupies volume. Okay, so what happens is that during time we have what we call silting, and so you have for a given volume you have a higher height here in the reservoir. That means that your reservoir is losing efficiency, okay, in terms of its storing capacity. And so periodically you have to remove this material in order to recover its original performance, because again the design was made assuming a given nominal volume here for the reservoir. Okay, so silting is a very important problem. It is related to OPEX, to maintenance cost of this power plant. Okay, so we're almost there. So combining these equations, okay, we have flow rates here that vary in time. We are going to adjust Q1, Q2, and Q3 in order to maximize the overall power. Okay, the individual powers are given by this formula. Okay, so the specific rotation goes here. Okay, so in Q, the individual flow rate and delta H goes here. And what I want to emphasize is here, those are conflicting effects, because you see that in order to have maximum efficiency, which corresponds to x equals 0.5, okay, you have to have this relation, a square root of Q multiplied by delta H2 minus 3/4 equals constant. Okay, in order to have, no matter what you do with the flow rate, if the corresponding height satisfies this relation, you have always maximum efficiency. Okay, but when you look at the reservoir performance, you see that when Q increases, okay, Q increases, of course you have a tendency to decrease the level here. If you increase the flow rate, this is going to decrease if A1 is constant. So in order to maintain nominal condition, it would be interesting to maintain this relation, and this conflicts with this. Okay, so that's the base of the problem that we want to solve in terms of the instantaneous optimization. Okay, so we have everything now in order to do the simulation. Okay, we want to adjust these flow rates in order to obtain a maximum, maximize this optimization function. And just to repeat, we want to maximize average power, because in the whole year this is going to result in a higher, a greater amount of total generated electricity, and we want to simultaneously minimize sigma in order to have more regularity. Okay, so let's see the optimization strategy. Okay, it's very, very simple. Okay, I'm going to explain here. It is written here, and I'm using only two variables because it's simpler to explain. Okay, so follow me. Okay, bear with me. You start by assessing, by stating that the flow rate Q1 is going to be this value and Q2 is going to be this value. Okay, then you make a random variation of one of those. So let's say that you step here. Okay, in your software you're going to test if this increases or decreases the objective function. If it decreases, you discard this variation. Okay, so you discard. If it increases, as here, so you see you're closer to the optimal. So if it enhances the objective function, you keep this variation. Okay, and that's it. Then you repeat the process in the other direction. This one, it increases. Okay, you keep the variation, and you keep doing this. So you go to the, you have a heuristics that leads you to the optimum. So that's what's going to be done. Okay, I'm going to show you how. Yeah, and that's the software. So let me explain, if I manage, let me explain the software. Okay, if you want to download this software, if you want to use this software, you send me a message and I will send you, or I can post the link on Facebook. So this is the control panel of this software. Is a simple software actually. So these are the reservoirs characteristics, okay, A, B, L, DH, and so on. Okay, and that's the total volume of each of these three reservoirs. Those are the turbines, okay, the parameters that define the turbines, okay, and these are results actually. So instantaneous power of each turbine, okay, and total generation. We see these. Those are the annual values. So those are the river and tributaries flow rates. They are here. Okay. Here are the individual flow rates of each reservoir. Okay. So this is Q1, Q2, and Q3. Okay. Here we have the volumes of each reservoir, the corresponding heads, okay, H, this is delta H, and this is efficiency of each turbine during the year, okay, this is, here you have time, okay, and well, the power, this is W, during the year, okay. So what we're going to do, I'm going to start the software in a moment. What we're going to do, we start from an operating scenario. For instance, constant flow rates in each, or almost constant flow rate in each reservoir. Okay, so this is Q1, Q2, and Q3. I'm going back one slide. So what we're going, this starting point here means constant flow rate during the whole year for the three reservoirs. Okay, and what we're going to do next is to vary each day's flow rate. Okay, because if I'm not mistaken, yeah, no, this is hours. So this is whole year in hours. Okay, so we are going to vary each the flow rates for every hour during the year. Okay, so we make a random variation here. If it enhances the objective, we're going to keep that. If not, we discard. Okay, and we're going to see the results here. Okay, so those are this graph down here is you're going to see the individual objective functions. Okay, and in this graph here is the total objective function, the sum of these three aqui. Okay, let me start the the software. You see here, it's varying the flow rates. Okay, it's varying the flow rates, and you see that the overall objective is increasing. Also, is increasing the individual objectives. Okay, but something interesting is going to happen. I'm going to pause the software. Okay, you see that. Well, let me go back a few. You see that we started, for instance, the green reservoir. I don't remember which one is which, but the green reservoir in the beginning of the optimization had very low efficiencies. For instance, 0.7. Okay, and during the optimization, you see here that the efficiency, individual efficiency, is increasing. Okay, is increasing. So that's why the overall efficiency is increasing. Okay, you see that very clearly. Okay, but something interesting is going to start happening right now. You see, I think it's the white reservoir. It's, oops, sorry, I changed slides. Sorry for that. Let me go to that point. You see here, let me pause. You see here the individual efficiency of the white reservoir is starting to decrease, and this is enabling the efficiency of the red and the green reservoir to increase further. Okay, so this loss of efficiency is more than compensated by this gain in efficiency of these two reservoirs. Okay, the white reservoir is the first one. Okay, so you see that you are sacrificing the first reservoir, the performance of the first reservoir, so that the other two reservoirs have increased efficiency, and that means increased generation. Okay, I'm going to accelerate to the end of the simulation. Okay, you see that here you reach kind of a maximum here for the year. Okay, and that's the conclusion. Okay, so what we can conclude from this is that due to the variations of these the main river and its tributaries, okay, and to the fact that the total flow rate passes, okay, so the white flow rate adds with the green flow rate and adds with the red flow rate and passes through the final reservoir. Okay, it's better to sacrifice, if you have to sacrifice one reservoir, it's better to sacrifice the first, because it has the smallest flow rates. Okay, so that's the conclusion. The point now is that what is the effect, okay, of that particular optimization function, because as I mentioned, this is completely arbitrary. Okay, so what we're going to do is to change this optimization function, okay, to see if by changing this optimization function we reach the same conclusion, which is this conclusion, to sacrifice the first reservoir for the sake of the following reservoirs downstream. Okay, so that's the first question that I want to answer now. Another question is, what is the effect of the size of the reservoir? Okay, because I start this class by saying that, well, it's better to have big reservoirs, but you have environmental problems. That's very typical of Belo Monte. You know, the original Belo Monte design, the size of the reservoir was much bigger. Okay, Belo Monte is something like this. You have the main river, you have the tributaries here. Okay, so it's flowing right here. Okay, and let's see. Let me change color here. So the original design, okay, had a so that's the dam. Okay, And let's suppose that the lake is going to be something like this. Okay, that's the original expected lake for Belo Monte project. Okay, that's the original lake. So this area, this flooded area, was too big. Okay, and due to environmental concerns, they decided to restrict the flooded area. How do you do this? Okay, you do this by making more reservoirs, more dams actually. Okay, so in addition to this dam here, you build here, and here. Okay, and then your lake is going to be something like this. Okay, something much smaller. Okay, I hope my drawing. So the lake, or the total volume, is much smaller, but it floods a lot less area. Okay, so the point is, that's okay, I'm not questioning this, but you have to be aware that this influences the overall system, to the point that it would be better not to have these hydroelectric power plants. That's my opinion, actually. Okay, it would be better to have I don't know, a biomass thermal power plant. Okay, but so the second question is to try to analyze the volume of the reservoirs are here. Okay, so we're going to compare the operation with small and big reservoirs to see what's the difference. Okay, and the number that we can use is going to appear here. Okay, just to be more objective. So this number that I'm emphasizing here is actually the numeric value of this number here. Okay, so let's see how it goes. Let me show you. Now I don't need to do the simulations. I'm just going to show you the final screens. Okay, so this one is, this case here is the, well, is always this. It is the same objective function that I already showed you. Okay, I'm not changing this right now. I'm investigating the size of the influence of the size of the reservoir. So this is the case for a small reservoir. Actually, this is exactly the same, the case that we obtained right now. Okay, in the previous slide. And so this small reservoir corresponds to these volumes here. Okay, and you keep this number. Okay. 40.240. Okay, so let's see. Now the things are, everything is the same except, I think I'm going to change this length here, 5 kilometers. I'm going to change to 15 kilometers. Okay, so 5 is being changed to 15. The total volume increases, and the rest remains exactly the same. So this is the large reservoir. Okay, the optimization function is the same. The river's flow rates are the same, and we get an increased overall generation. I'm going back one slide. So we had 40. Okay, that's our numeric value for our optimization function. And simply by working with a bigger reservoir, we have an increased generation. We can also see this in terms of the average power, okay, and the total energy generation in gigawatts, okay, and in megawatts. Okay, so we had 1,000, I can't see this, 1,585 here, and we have here 1,538 gigawatts hour. So we managed to increase here the total generation. Okay, simply by working with a larger reservoir. Okay, so that justifies what I'm saying, that it's better to have bigger reservoirs. Okay, so now let's see the influence of the optimization function. I'm going back one slide. So instead of adding the terms, yeah, go on.
If you increase the size of the reservoir, how about your turbine. You need to buy because perhaps the capacity may not be, I don't know if you have any effect on the turbine.
Sorry, I didn't understand what?
My question is if you increase the size of the dam or the volume.
The volume, okay?
Yeah, the
That's,
volume. Yes. Then how about the turbine?
Turbine.
Not any effect on it.
Well, everything is the same because the turbine is chosen from the nominal values, which are the annual averages, and this is not being changed in this simulation. Okay, so the design does not change by simply changing the size of the reservoir, the volume of the reservoir. Okay. So I understand your question because, well, if you're varying the reservoir, you should change the design and the choice of turbine. But as I explained it too quickly, possibly, because as I explained, this is chosen from the nominal values, which are not being changed here, because especially this, the flow rates are not changing and the heights are not changing. So DH is the same, 50 meters and 50 meters here. Okay, you see? The point is that with a bigger reservoir, you can use its height. Okay, so I don't know if you see here, but the heights are very less. Okay, so you see that with a bigger reservoir, the height of the reservoir does not have to vary a lot to accommodate these variations here. Okay, so that's the point. You keep the height constant, and that tends to produce a higher instantaneous efficiency. Okay, because you don't deviate too much from the nominal point with a larger reservoir. That's the point. So the next slide compares a different optimization function. So that's the same evaluation. So now instead of adding up all the terms, we're multiplying them. So the effect is exactly the same. Okay, no problem. And we get the same conclusion. The number here is different, but the conclusion is the same because the number is different because the formula is different. Okay, so that's the result with a small reservoir, 2,278, and this is the result with a larger reservoir, 6,640. Okay, and well, the amount is the same. Okay, so you see that it's better. I think I have a third optimization function. Now I have the average power to the third. Okay, and still the result is the same. It's better to have a bigger reservoir. I think we can see this. Yeah, we have to compare this number. Okay, so 18 compared to 19,000, or it's too small here. 192 hundred thousandths. Okay, compared with 180 hundred thousandths. Okay, so it's always better to have a larger reservoir. Okay, yeah. So in that let me see if I still have that. Yeah, and that's why by reducing the size of the reservoir in Belo Monte, I sustain that. I don't know if we make the proper calculations, we might conclude that it would be better not to construct this reservoir at all. It's very good in terms of civil engineering because you have more civil engineering structures. You have to spend more concrete and so on. So for those guys that supply concrete, for instance, a very good business, but for the electricity generation, it's not good. Okay, so that's my point regarding Belo Monte. Okay, now just to conclude, that's the final slide. Yeah, I managed. I have still 5 minutes. Sorry. Yeah. Okay, so that's the last slide, just to justify what I call the functionality of the reservoir. Okay, functionality of the reservoir and functionality of the reservoir in a system such as this, as I'm showing. You have intermittent source, so you have wind power here. Okay, let me get my pointer. You have wind power, solar, but the point is that these sources are intermittent. Okay, so you can use those reservoirs, okay, to compensate for these variations. We can see this depicted here. Okay, so the red curve here represents the power supplied by these intermittent sources here. So it varies. Okay, and the black curve here represents the power supplied or absorbed. I'm going to explain this in a moment. Okay, so the black curve here represents the power supplied or absorbed by these hydroelectric power plants. And the idea is that the sum of the red curve plus the black curve gives you a straight line. Okay, so a very constant supply of electricity, and that's what we call dispatched power. Okay, because we have to be constant here. So the lens here represents the power that is being supplied in this point here. Okay, and explaining what I mean by absorbed, because there you can actually do the following. If you have excess, if you have a lot of wind and a lot of sun, so you have more power than what's being demanded here by the consumers, you can use this power in order to pump water from here to here. I know at least one power plant like this in Bahia, here in Brazil. Okay, they have windmills and also have a small reservoir, and if you have excess power, you use this power to pump water from here to here. And when you need, if wind stops, for instance, you can use this water to generate through the turbines. So in addition to the turbines, you can also have pumps. Okay, you can also have pumps, and you, as I was saying, you can use this excess power in order to store this excess energy in form of water stored in the reservoir, which you can use to generate electricity if you don't have any more of this excess power. Okay, so what I call functionality of the reservoir is becoming increasingly important, okay, in a scenario in which you have several sources of intermittent performance. Okay, so the point is not to generate a lot of electricity. I showed you, we made calculations that the potential for growth in terms of generation is very limited for hydropower. Okay, but in my opinion, the role that they are going to play is not in terms of supplying power, okay, to the system, but in terms of compensating the fluctuations of these intermittent sources. Okay, so that's a very important role, because you have very few systems that are able to cope with this task, because the quantities are very high. You cannot use, for instance, biomass to do this. Biomass is a very stable source of energy. You can store, you store biomass, for instance. You can burn more or less in order to generate more or less electricity, but you cannot store the equivalent of kilometers of dozens of cubic kilometers of water in terms of energy. That would be too much biomass. Okay, so the reservoir is very important because it is capable of storing very big quantities of energies, and there are very few solutions for this problem at the scale that they occur. Okay, so this is a very important point in my talk today. The importance of these reservoirs, what I call functionality. And Brazil has a very significant advantages because we already have a very huge number of reservoirs, as I showed you, okay? But they are being used for generation, okay? When we start increasing, we start investing in other sources, especially those intermittent ones, we're going to be needing a lot more of this functionality, okay, in terms of stabilizing the supply of energy. So they should be playing a more important role. In other words, just to finalize, it would be very interesting to have very, very large reservoirs, even if they don't generate much electricity, large volumes of electricity, but larger reservoirs enables you an overall optimization, okay, as I show you in this small simulation, okay? Okay, that's it. That I wanted to conclude with this slide and with this statement regarding these hydroelectric power plants. Okay, if you have some questions, I'd be happy to answer. And my throat is already in its final moments. Okay.